So my name is Tom Panozzo. I work for Aunalytics in South Bend, Indiana. I'm Chief Technology Officer and one of the founders of the company. We are I would say, a fast-growing company in South Bend that runs data centers and also develops analytics platforms and software for the healthcare and banking industries. All right, so who we are. So Aunalytics is a cloud platform company in the Midwest. And we develop high-end algorithms and run it on a home built or our own platform that we've developed using a combination of open source products, our own developers, and some commercial products, of which Alluxio is one. We have a digital transformation model that we use. So we bring in data from diverse locations across the country from different customers, and we provide on-demand access to it. So basically a platform that can ingest, process, and deliver back insights to customers in primarily financial and healthcare industries. Okay, so our primary solution is branded Daybreak, and it's about 5 years in the making. It's comprised, as I said, of different technologies. Alluxio is one of those. It's comprised of storage technologies, processing technologies. A lot of this came out of the Hadoop environment from years ago, and we've used those things to develop a product of our own. Excuse me. Daybreak, as you see here, it's a data platform. And when we say powered by financial industry intelligence, what that means is we've taken years of knowledge from individuals and companies in the financial market, and we've developed algorithms and smart features based upon those things to enable and deliver a variety of analytic solutions across the banking enterprise. As I said, we do healthcare as well. This presentation will focus mostly on the banking side. So, and I'm going to spend a little bit of time on this, but this just somewhat demonstrates the flow of data that we have to use. So we're bringing in data across different systems. So you can see, like, we've got a core system, a banking core system. If you've worked with banks at all, they always have a core type system. They may have a lending system, mobile banking, their ATM system, and so on. And these can be across their enterprise. They can also be service providers that they use, and so on. And all of this data is disparate. So it's across all of these systems. Seldom is it clean. It's often very dirty. There's different people with different names, or they have a junior in their name, or things addresses might be wrong, and so on, across 7 or 8 different systems. So we bring all those in. Most of it is transferred either via the internet, or we'll bring it in directly from feeds into service providers. We'll run it through our Daybreak platform, of which Alluxio is a part of, and we'll deliver it back to customers in any way that they want to consume it. So Tableau, Power BI, Salesforce, they can connect directly in with their SQL tools. They can use Python if they've got programmers, things of that nature. And I know that this looks simple. Actually, the most complicated part of it is the center part, the Daybreak part, and that's what I'll describe to you. So one of the things that we do is we say, let's set it up so the customers can access all their data in one shared location. So you may have a bank with 10, 5, 20 systems. All of them are different. Every person can access most of these systems, but they can access them individually. So what we will do is we'll bring all of that data into one. It'll run through hours or minutes, however long it takes, of joining data, processing data, adding other fields to it, doing calculations, and so on. And we will put that into one master data set that the customer can then view in any way that they need, and it's customized to them. So they have everything that they need in one specific place. So one of the things also that we will do is set this up so the data is transferred and updated in real time, or as close to real time as possible. Sometimes some things will run overnight, but generally we shoot for as real time as possible. And the data, when the customer is ready for it, is updated daily or hourly. They can set whatever cadence they want, depending upon their specific needs and so on. But it's always available when they need it. So as opposed to having to do what banks would normally have to do, which would be to go to their IT department and ask for an output of something that they have to mix with an output of something else and spend hours and days doing that. When we set this up and run it through our platform, it's available all day, every day. And usually we set it up so that it's, most of the jobs will run at night, and all of the data will be available in the morning for the people to use, and then updates throughout the day as need be. But it basically puts everything into one place from many sources, and it does it on a cadence that it works for each customer. One of the things that differentiates us from other service providers that are doing this kind of work is that we employ experts in the fields where we are processing the data in. So we have banking experts on staff. We have a number of people that have worked in the banking industry for many years. We've worked with them to develop the algorithms and the tools that the individual people will use. When a banking customer decides to contract with us, they're not just contracting with us as a service provider that provides a platform that they can use and they have to know everything about and make work for themselves. We really focus on delivering a workable data set to someone as quickly as possible. So as opposed to just putting them in a situation where they're transferring data into a data lake of some sort, and then their people have to determine all kinds of different things from how to join it, what data is important, what kind of questions they might want to ask, things of that nature. We have developed all those things in-house. We developed them in concert with customers. As customers have new questions or things that they would like answered, we will incorporate that into our platform as a whole for other customers to benefit from, and so on. So that is a big differentiator in the industry in that we employ people to sit alongside with these banking customers and assist them in this quest for analytics. All right, so when we set out to do this, originally this was about 4 or 5 years ago. Hadoop was the thing, and we set out to design a platform that would allow us to process data in real time from many sources. We didn't know what the challenges would be at the time, but it was one of those, you need Hadoop, or you need things of that nature, if anyone remembers that time period. And that was where we started, and of course quickly learned that it's a lot bigger than that. There's a lot more things you need, and to be competitive or to be even able to deliver what we deliver, it takes 10 or 20 different types of systems that we have had to integrate into this. Most of them flow through Alluxio, which is, and I'll get into how that fit into our needs and so on in the following slides. Okay, so the way that I structured this is that to say, we've got requirements for, we started out with a set of requirements that we would need in order to deliver the things we had, or that we wanted to deliver. Now, of course, you learn as you go, because we're developing something from nothing. So we started off with things we thought we would need. Hadoop was one of them, and so on. But really what we needed to do was create a situation where we had data availability across a diverse set of dynamic services. So we've got all kinds of services. We've got services that come and go. We have services this year that we didn't have next year. There's all kinds of things in the industry that are being created, especially in the Apache type arena, for data science work that are new and so on. So we had to create a way that we could bring those in as part of the platform, and it needed to be diverse in that way, and that these things could simply bolt on and so on. So Hive was something that we used a while back. That's going away. An example of new things: Neo4j, Exasol. Those are both new. Hadoop is a big part of the platform, and Apache Drill is another large part of it. And as I think you would see a lot of the typical things on this slide, Spark and so on. These are some of the mainstays that we have, but there's a lot more, and we can go through those as well. So when we when we were designing the storage for this environment, we realized that it has to be parallel. And we bring in a lot of data from different customers all the time. Every night we bring in, you know, I wouldn't say terabytes yet, but many gigabytes of data nightly. And a lot of this data needs to be processed, but a lot of it actually ends up being historical. And that actually has to be, we can't get rid of it, but we must, but we have to store it, but we don't need to be able to process all of it all of the time. So but we did realize that in order to do the amount of throughput that we needed, we would need a parallel file system. So that led us into a whole type of evaluation of storage type platform tools and products. You know, if anyone who has worked on this, you've got your typical parallel type file system, which is, you know, your GPFS or DDN or any of those kind of guys that are running and building those kind of systems. Cray makes a system that we looked at. Those are parallel by nature, they scale by nature, but the way that they work is they're generally all fast all the time. They do advertise things like tiering, where you can have, you know, fast disks and slow disks, and it'll move the data around. But we found the cost benefit of that to be negligible, and the overhead cost is high. You're paying for their technology to do those things, and even in those cases when you want to move data from one place from a slow storage to a fast storage, it's not really that fast to do it. I mean, it's not something that you would do in real time if it's a lot of data. So Alluxio, as it's deployed, is also parallel in nature, but the way that we've deployed it is that the data that's in use is fast, and the data that's not in use is less fast, I guess you could say, in these days, but certainly not as fast as the data that's in Alluxio. Alluxio is also invisible upstream. So it's somewhat of like an obfuscation layer between all of our clients, all of our users, and the actual underlying storage. And that allows us to use whatever underlying storage we want, and so on. Also allows us to scale based on performance. We can add Alluxio nodes when we need them, and that in no way is tied to adding storage when we need it. So we could bring in a petabyte of storage that needs to be historical, and that does not necessarily mean that we need to add any more to the Alluxio side of things. So that goes to say that the scale is decoupled from the amount of storage, which was a big deal to us. So this is a little bit of a complicated type slide. I don't necessarily love these, but this just gives you an idea of all the things that are down in our managed infrastructure layers. So if you look at the bottom, you've got our storage, which consists of Hadoop HDFS, NFS, other types of storage, and so on. We've got other things underneath here. We've got data going to Graylog and so on. We've got MongoDB and so on. And all of these things will flow through Alluxio. So everything in the upper half of the slide is effectively all of our, represents all of our tool stack that accesses the data underneath. But everything flows through Alluxio. And so it really is center to everything that we do in the environment. Just to give you an idea, because I thought that this was a reasonable way to do it, is this has been a journey. So we started building and designing this platform about 5-6 years ago, and as I said, we started with Hadoop. So how we got to Alluxio was a bit of a process, and really was a process of understanding what we needed to do what we wanted to do, and finding many products that got us 80% of the way there. So our legacy Hadoop platform, which would be a typical Hadoop platform, is we would have, on the left side here, we've got multiple clusters. So we had so many jobs that we had to run every night. And because of the nature of this, one point I should make is that, even though we got 24 hours in a day, when the banks end their day, 10 o'clock or whenever they're done processing, we need to transfer the data from them at that point. And then it has to all be processed throughout the night. So we really only have 6 hours with which to process the data of all the customers. The other 18 hours, most of the infrastructure is still in use, but it's not running anywhere near what its capacity is, because all of our work is focused to the night hours. So we could have had one big cluster, but we couldn't do that for the parallelism we needed. So we ended up with Hadoop cluster 1, 2, 3, and so on. And the Hadoop cluster was where all the heavy lifting took place. So you had a lot of nodes. Every node had to have a lot of IOPS. So you had 24 or more hard drives, usually SAS. They used to say you could do it with SATA. That was not our experience. So we ended up with a lot of very expensive nodes with high-speed disks, data stored in triplicate across many clusters, and so on. And all of that was being run in our small containerization platform. So we had Kubernetes, and our product runs in containers on Kubernetes. So we basically orchestrate all of the jobs that run and so on. So we had a small, low volume, low lift Kubernetes platform that really just did all of the commands, and all of the actual heavy lift and all the work happened in Hadoop clusters. So that worked, except for the fact that we had these limitations. Data stored in triplicate. So that was something that we always would have to do. It requires very high speed storage because everything, when it runs, it has to be fast. The storage, in addition to being high speed, has to be able to have a lot of IOPS. So you require many spindles. You can't just buy high speed disks. You need high speed disks and a lot of them. And Hadoop nodes are costly. So contrary to what was marketed to everyone at the time about Hadoop being inexpensive and on commodity hardware, the reality is the commodity hardware for Hadoop nodes was $15,000 a node. So it wasn't really a practical thing to scale massively, at least in our case of being a startup company and so on. And then the most important thing here is that the storage is always performant. So it's still performant even when you're not using it. All the data is always stored in Hadoop. It's always there. You could always run very fast, big workloads on it. But for 18 hours a day, it's really just sitting there being stored. So that was not a great use of assets for us. So let me just move this here. We came up with a couple of options here. And like I said, this is how did we get to Alluxio. But the first option was to use commercial boutique storage. And what that would be is anything from, I don't want to say vendors, but everybody knows the parallel file system vendors. It could have been anything from IBM's GPFS type stuff to Lustre, to any of those kinds of things. Massive learning curve on those if you're going to homebrew that. But what that would be is we'd have extreme performance storage, and it would have to be, these things are engineered clusters that are designed and supported by large scale vendors. They're extremely high IOPS and so on. They're extremely expensive. So lots of performance storage, lots of performant LAN, usually fiber optic if you have to, if you're going to run really high performance things, lots of replication and so on. And then what we did here is we moved all of we ran our Hadoop processing nodes, or we would run our Hadoop processing nodes, and we would access the data in the form of LUNs that were connected to the nodes. So the nodes didn't have internal hard drives. And we would connect to that and use that storage and so on. Well, the issues with that is that the storage is extremely expensive. There's no more expensive storage than parallel file systems that I've come across. All the nodes in this case have a singular purpose. So everything is what it is. If it's a Hadoop node, it's going to run Hadoop. That's all it's going to run. When you're not using it, you're not using the asset. It requires high-speed dedicated network, many spindles. You're married to the vendor. So you've got, for your underlying storage, whoever you pick, you're with them for a long time and so on. And then your data is on high performance storage always. So again, when it's sitting, your $1 million storage is doing nothing for you 18 hours a day. So again, the storage is still performant even when you're not using it. So same kind of thing. This is another, most of what I just said, but this is another exercise that we went through, open source storage proposal, and that would be Ceph or Lustre, should be GPFS, and so on. Same thing, same issues. Ceph, we looked at Ceph, we looked at home growing a Ceph cluster, and realized that that would be great, but I need to hire 3 people to keep it healthy, or buy a very expensive support contract. It was not something that made good sense in our case. And even in that case, we still everything was still dedicated. Hadoop clusters were Hadoop clusters. That's all that asset was, and so on. So it had all the same limitations of boutique storage. So the final design choice that we made was Alluxio. And I've got a number of slides here kind of outlining how we came to that conclusion and why. But just to kind of outline it here a bit is, we've got NFS backend. We've always had an NFS backend. We're a data center, we're a cloud service provider. In addition to being an analytics service provider, we've got all kinds of very reliable storage that we make available to customers. So we've got, the usual suspects, the NetApps and the EMCs and so on. We've got all this storage. We've got lots of it in SATA. So it's big, cheap and deep, I guess people would call it, and so on. And all of that is NFS. So we've got a bunch of this stuff, and it's way more cost effective. It's not nearly as performant as boutique storage would be, but it is certainly reliable. And it has a lot of features that are valuable to you, like replication and deduplication and all those kinds of things. But it's also very cost effective compared to other things. So, but the problem with it is that the transfer speeds are average. I mean, unless you're buying their top of the line product, which is still not as fast as boutique storage, you still end up with average transfer speeds, because there's a limitation of the way their architecture is, that you have storage heads, and there's 2 of them. They can only go so fast, and they will never scale in a parallel fashion like a true parallel file system will. So that's what that's why we chose this. So we've got a number of NFS backends, many I should say, and we designed an Alluxio system to sit in between that. So we would consider that to be extreme storage speed. It's an abstraction layer between all of our other services and all of our storage. So as we built it, and these are measurements that we did, but it's 200 cores. Our system is got 6 terabytes, and it's all flash. So we chose to just do it the full memory based Alluxio, and we've been able to push 12 million read IOPS and about 40 gig per second sustained read performance out of this thing, assuming that the data is in Alluxio. So, Alluxio allows you to access your storage for data that's in it or not in it. If the data is not in Alluxio, it has to go get it. So I'll touch on that a little later. But if it's in Alluxio, in RAM, on the proper network, the amount of speed that you can read out of it is extreme. I would say in excess of what you could do with most parallel file systems. So as I said, it's a scalable caching layer. It's all RAM and flash based. So we have no spinning disk in this layer. And what it does for us is it compensates for lower cost underlying storage. And it replaces our Spark, it replaces our physical HDFS. And what we've done with this is we have connected this, we've eliminated Hadoop nodes, and we've moved all of our heavy lift over into Kubernetes. So where we used to have 3 or 4 Hadoop clusters they were 9 or 10 nodes apiece. So you're talking 40 nodes. We've got effectively 20 Hadoop clusters on the same amount of hardware. So by moving Hadoop and all of what it does for us into containers and running it all in RAM and connecting to Alluxio that's all in RAM, we've been able to get a 5 to 10-fold utilization increase out of our underlying hardware that we have. So to talk about this a little bit more, as I was saying, our Kubernetes platform now handles all the heavy lift. So whereas it used to be the Kubernetes platform just sent the commands over to HDFS, over to Hadoop, and asked Hadoop to process on its behalf. We've moved all of that into containers. So we have I'm not going to call it large, but powerful for sure, Kubernetes platform that we have many Hadoop nodes in. And the asset, the hardware asset there is very flexible in that we can spin up Hadoop clusters. I mean, we can spin up a 20-node Hadoop cluster in 2 minutes, and we can spin it down. So the amount of, and we can put another one in its place, or we can have 10 of them running at the same time, as long as we have enough memory and CPU to support that. So all of the heavy lift goes there. The only catch to this is that if you're going to have that much processing capability in a Kubernetes cluster, and you want to process data, the data has to be accessible to you very fast. So that's where Alluxio sits. So if you see on the left side here, we've got object storage as well, NFS. Hanging off here, we've also got some GPU resources that we use to do some model training and so on for some artificial intelligence things. They all connect into the Kubernetes system, and the Alluxio data cache effectively sits in between all of it, and so on. So our Kubernetes, our platform now is about 25 servers. It can scale to thousands and so on. So that is a major shift from the way that we were able to do things before. So one of the big deals with Alluxio for us is they have adaptive read-write methods, and we've taken full advantage of that. You don't have to. A lot of people, I guess, don't, but it was a big deal to us. So what that means for us is that we take a pre-staged read methodology. So even though we're loading many gigabytes of data onto our low performance storage, what we will do is any data that we know we're going to need to process in a high speed fashion, we will pre-stage into Alluxio. So when the data lands from the customer on our low performance storage, we'll send a command to Alluxio prior to needing it to say, hey, go ahead and load this data. So it'll pull the data off of or a copy of the data off of the low performance storage into its RAM. And then when we need it, it will be in memory. So there's 4 of these. And one thing that I think is really a neat thing that they did is that you can control these. So you can embed a command in your write string to tell Alluxio how you want this data to be handled when it gets it. So there's 4 of these that we use, but there's and it's, you can read about this online, but effectively you've got write to Alluxio only. So when Hadoop is processing data, it's writing a lot of temp files, and we actually use Alluxio for those temp files because it's so fast. So in the write commands that we send from the Hadoop nodes into Alluxio as these temp files are being written, we will say, don't push these down to the underlying file system. Just run it in RAM, and then those files, they can go away. So we get extreme speeds that way. The next one is write through. So we rarely use that, but that's just write through Alluxio and push it right down to the NFS. And then a couple that we use very important is write back to NFS. It's called async through. And what we'll do is say, write it to Alluxio, and Alluxio will send us the acknowledgement back, and then we forget about it. That write is done. And then we leave it up to Alluxio to push that data down within seconds or minutes to the underlying storage. But we're not dependent on the underlying storage for the acknowledgement. So most 95% of the data that we write to our underlying storage goes through Alluxio. It's done in an async through mode, so that we can interact with our storage at extreme speeds, and we don't care at all about what the underlying storage performance is. We just let Alluxio handle all of that. And then we've got write to UFS only, where it writes through. We rarely use that, but the main point here is that we can embed the write modes into each write, and it allows us to tune every write that we have for maximum efficiency. We don't have any data going anywhere where it doesn't need to be transferred, and so on. So that's an important functionality. And I can skip through this. So at the conclusion here, is that we determined that we're going to have mass quantities of historical data that must be stored, but a much smaller amount of data that must be processed daily. The relatively small amount of data that we must process daily requires parallelism. So in our case, we can add more Alluxio nodes as we need it to be faster, but we require parallelism of the underlying storage in order to run in the speed that we need it to be. And then beyond that, say all data must be quickly available for high-speed processing if it's required, but allows for in-memory storage performance levels in a controlled, tunable, and independently scalable way. So that really is why we chose it, is that it allows us to have whatever we want on storage on the back end. It allows us to control our performance levels with the way that we write data, and it allows us to scale our performance independent of scaling our storage infrastructure. So we can add a petabyte of storage and not add any performance. We can add another couple hundred gig of performance and not add any more storage. And we can tune these to our specific use case and adjust it in a dynamic way as we grow.